Hey everyone, in this Chem Help video we're going to look at multi-step equations, sometimes called serial equations, which is a type of chemical calculation where we're linking compounds in multiple steps. So this works well for industrial processes where one step is not enough to complete the equation or the process. From a chemistry point of view they're fairly straightforward. We're still dealing with moles of unknown and moles of known, but because we're linking between different equations they can be a bit tricky. So we need to practice them and follow a very simple process to get them right.
So let's have a look at what we know so far. We know about single-step equations. So in Year 11 chemistry, we learned to determine the number of moles of an unknown substance from another known substance. What we needed was a correctly balanced chemical equation and the following general formula, which was the number of moles of any unknown substance is the coefficient in front of the unknown over the coefficient in front of the known times the number of moles of the known. And from that, we can determine anything we like. So, for example, if we had 3 moles of zinc, how many moles of zinc phosphate would be produced if we used excess phosphoric acid? So first of all, we need the equation, and it's going to be correctly balanced with the right coefficients. So you can see there's 3 in front of the zinc, 2 in front of the phosphoric acid, a 1 in front of the zinc phosphate, and a 3 in front of the hydrogen gas. What we're concerned with is the zinc and the zinc phosphate, how are they linked together? Now, there's a 1 in front of the zinc phosphate and a 3 in front of the zinc metal itself. So we know it's 3 moles of zinc. We know our general formula. I've just condensed that just to get rid of the word coefficient, but you know what I mean. We plug the values in, so the number of moles of zinc phosphate is 1 over 3 times the number of moles of zinc, and we therefore plug our numbers in, and we have 1 mole of zinc from 3 moles of zinc phosphate from 3 moles of zinc. So you can do that for anything. You can take that a step further, and we did in Year 11, and you start with masses, or volumes of gas, or concentration in solutions. You determine the mole relationships, calculate the number of moles, figure out the mass, volume, gas, concentration, anything like that, and we can basically use this flow chart. So as you can see in the chart there, you can go in through any avenue you like, go through the central equation and come out through any avenue. So you can start with mass, go through the equation, come out as concentration. Start with concentration, go through the equation, come out as gas volume. Go through volume, go through the equation, come out as mass. So you can do anything you like, and we got quite good at those. And the next step above that was limiting reactant calculations and doing stuff with those as well. Okay, however, real life chemistry, things aren't always that simple, unfortunately. Many processes take place over a number of different steps. Might be 2, might be 3, might be 4, might be 5, might be even more than that. So here's an example. To produce sulfuric acid from iron pyrites, you need 3 separate and distinct steps. First of all, you take the iron pyrites and react with oxygen, forms iron oxide and sulfur dioxide. Take the sulfur dioxide, react it with more oxygen, forms sulfur trioxide. Take the sulfur trioxide with water, and you can make sulfuric acid. So 3 distinct steps. So if we look at those equations as 3 steps, if we just got our standard formula, unknown over known times number of moles known, and just used it blindly, we would get the number of moles of sulfuric acid is 1, that's a 1 in front of that sulfuric acid, over 4, because it's in front of the pyrites, and there's our formula. But that would be quite wrong. So if you did that, you'd get a totally wrong answer. That's because balancing coefficients only apply to the equation that they're in, not the other equations. So that 4 in front of that pyrites is applied to that equation only. It's got nothing to do with the third equation at all. We're trying to conserve mass in each equation, but not between equations. So how do we do it? What we need to remember is that there's an 8 there, and there's a 2 there. Now they're separate equations, obviously different numbers. All right? But the thing you've got to remember is that they're the same number of moles. They're just balanced differently to the equation that they're in. Think of it this way, production is like a conveyor belt. The factory is not going to throw away 6 moles going from step 1 to step 2. They're going to take everything from step 1, move it all into step 2, and continue the process. Because industry and production is all about maximising profit. They're not going to lose anything. So the fact that there's an 8 in one and a 2 in another only applies to the equation they're in, not the next one over. Okay, so how do we do it? Some people will tell you to balance and smash all 3 equations together to get one final balanced equation. It might work, maybe. Don't do that. It's messy, it's prone to errors, and it's just difficult. It wastes a lot of time. that would create extra work for you, and nobody needs that. We don't need extra work. We're trying to get through a calculation as quickly as possible. Right, so this is how I recommend you do it. Write your 3 equations out. Once you've done this step, you never need these 3 equations again. Okay, so first step. Identify the substances that link. They're the conveyor belt steps, if you like, in the process. So in this case, sulfur dioxide moves in from one equation to equation number 2. Sulfur trioxide goes from equation 2 to equation 3. All right, like that. Now what we do is we place a 1 under the chemical that you know. How much you have means nothing at this stage. If they said you had 455 kilos or 6 tons, irrelevant at the moment. Don't worry about the amounts. We'll do the amounts later. Just take a 1 and put it under the thing that you know. That's it. Just do that. Right. Now, use unknown over known to figure out the linking compound. So, that's 8 over 4 from that equation. And 8 over 4 simplifies down to 2. Now, this is the tricky bit and the important bit. Take that 2 and take it all the way from equation 1 and put the whole lot in equation 2. You ignore the coefficients. They don't mean anything. They don't link each other. Right? So take that 2 and move it there. All right? Now, determine the linking compound. In this case, the SO3, using unknown over known. So 2 over 2 times 2. So 2 over 2 is 1. 1 times 2 is 2. So it stays to be 2. Now take that 2 moles and take it again to equation number 3. Don't touch it. Don't change it. I can see that there's a 1 in front of SO3 in the third equation and a 2 in the second. Don't worry about that. They're not linked. Take the whole 2 from equation 2 and put it in equation 3. Then take that 2 and use unknown over known again to determine the number of moles. So 1 over 1, because that's what the coefficients are, times 2, and you get your number of moles, which is 2. So what that tells us is that 1 mole of FeS2 equals 2 moles of sulfuric acid. So there's our unknown, there's our known, and what we can do is we can write one final equation. So we've got 3 quite complicated equations replaced with one really simple one, and that's what we want. And then we just carry on as normal. So if someone said you've got 455 kilograms of iron pyrotes, how much sulfuric acid would you make? Well, you convert 455 kilograms to grams and then convert that to moles, plug that in the equation, times 2 over 1, spits out the number of moles of sulfuric acid, and then you can say, oh, the volume is, or the concentration is, or the mass is, depending on what you've been asked. Easy. Now let's try another example. If we look at these 3 equations, we're using ammonia to make nitric acid. So if we asked ourselves how many moles of ammonia would be required, that's an unknown, to produce 4 moles of nitric acid, that's a known. How are we going to do that one? Okay, so give a tick and a question mark. That helps us keep record of what's going on. Now notice in this example, we're starting at the bottom and moving back up to the top, not the other way around as was in the previous example. Okay, so let's do it. Right, first of all, we need to identify our linking compounds. Now the nitrogen monoxide is in equation 1 and equation 2, and the nitrogen dioxide in equation 2 and equation 3. Alright, so we start off with our known and give it a 1. As I said before, it doesn't matter the actual amount that you've got. We'll worry about that afterwards. So first of all, 1 mole of nitric acid. Now how many moles of nitrogen dioxide does that make? Well, unknown over known, 3 over 2. There's a number of moles of nitric acid. Now this whole amount of NO2 rather goes to the next step above. Take it up there. Don't change it, don't touch it. Alright, how much NO, nitrogen monoxide? So it's 2 over 2 times 3 over 2. 2 over 2 is 1, so that means there's 3 over 2 there. Take the whole amount back up there, 3 over 2. The 2 there and the 4 there mean nothing. They're totally irrelevant. They're linked. They're not linked at all. They're for different equations. How much ammonia? Well, it's 4 over 4 times 3 over 2, which is essentially 1 times 3 over 2, 3 over 2. So how is ammonia and nitric acid linked? 1 mole makes 3 over 2, or 1.5. So the number of moles of ammonia is 3 over 2 over 1 times nitric acid, or we can simplify that down to get rid of the 1 on the bottom. Number of moles of ammonia is 3 on 2 times nitric acid, or 1 over 5. And we can get rid of all the equations. So they're the basics. You're going to have to practice those a bit and apply them with some moles and some masses and some concentrations and those sorts of things, but hopefully that will help you out a bit. And we'll see you in the next video. Okay, thanks very much.